Okay, testing, testing. All right, good. Welcome to Astronomy. Oops. Welcome to Astronomy 405. We're picking up our discussion of small bodies, and this time we're going to talk about the composition. So we're focusing on asteroids, a little bit about comets, and small bodies, including meteorites as well. So we'll talk a little bit about the composition of asteroids and trans-Neptunian objects. Now, just a little bit, one of the major things that we can do with small bodies that we can't do with like Mars or Venus is we have samples from most of those. We have a few meteorites from Mars and the Moon, but from the asteroid belt, we have meteorites. Now, the trick is that we don't. The problem is not that we don't know what's in meteorites, because we do. The problem is basically matching meteorite to asteroid, and we're going to talk a little bit about that, but first I need to summarize what we know about meteorites. So some differences. We divide meteorites into falls and finds. Falls are when you see a meteor, you see the piece of rock or whatever coming in, and you see it hit and you pick it up and it's a fall. Now, if you are just wandering around, you find a strange rock, and it turns out to be a meteorite, that's a find. Now, falls tend to be a better measure of what's out there because they are just giving us a direct sample of what hits Earth. A little, and what doesn't break up in our atmosphere. Finds tend to be biased towards rocks that don't exist on Earth. We tend to find, for instance, more iron nickel meteorites, more metallic meteorites than are actually represented because they're very distinct. You pick up an oddly heavy rock and you're like, this is weird, I want to get it checked out. There is one exception, which is Antarctica. A lot of meteorite expeditions gather meteorites in Antarctica, and that's because they're pick areas where the ice is kind of concentrated, the amount of meteorites that fall there, and there's not that many local native rocks in the area where they gathered them up. They're all buried under the ice, so it's much closer to the statistics we have for falls. So what is it made? The other way we look at meteorites is, what are they made of? So you get three basic categories. Iron, contain iron, nickel, and related elements that dissolve well in molten iron. We call them siderophiles. Then you have stony meteorites. They don't have that large amount of iron and nickel. And then stony irons are kind of in the middle. They contain both silicates, rocky minerals, and iron, and they do it in a macroscopic way. There are classes of stony meteorites that have some iron, but they tend to be mixed in microscopically. So let's go through some of what we find with these meteorites. So let's start with the irons. So they tend to be pretty pure iron and nickel, and there's some thought from archaeologists this was one of the first ways humans started working iron, was to find these meteorites. They didn't have to dig up iron ore and figure out how to turn it into metallic iron. Now, one of the cool things about this is they have there's two basic iron nickel minerals that form, and they crystallize slowly, just like any other rock from molten. And the crystallization pattern looks something like the picture at the right. We can see the crystals in the meteorite by just basically cutting it open and treating it a bit with an acid to kind of etch the surface a bit to bring out the change in texture. These are called Windman-Satin patterns. And the size of the crystals, just like with igneous rocks, can tell us how fast this meteorite cooled, which then tells us what was the parent body like. Now here are some stony irons. We have two basic types, mesositerites and pallasites. And you can kind of see the difference between the rock and the metal. These are really rare and they're often really pretty. And stony meteorites, these are the most common based on falls. We tend to find more, selectively more irons and stony irons in finds just because they're very distinctive. You don't often see chunks of metallic iron nickel alloy on the surface of the Earth. Now, there's two basic classifications of stony meteorites. We're going to subdivide this. Achondrites and chondrites. So basically, do they have something called a chondrule is our distinction. Achondrites look a lot like the Earth's crust and mantle, or Mars's the moon's. So we can kind of imagine that achondrite stonies, irons, and stony irons all represent the different layers of a body like Earth or the moon that was broken apart. The iron and nickels from the core, the achondrites are from the mantle and crust, and the stony irons from the core mantle boundary. You can tell this because just like iron selectively had those siderophile elements that dissolve well in iron, achondrites tend to have elements that are either lithophile, dissolve well in rock, silicates, or chalcophile, they dissolve well in sulfur. The word comes from the name for copper. Or these tend to be the elements that would separate out and be in the core and the mantle. So they look, again, rocks on Earth and Mars also look like they have more lithophile or chalcophile elements. So achondrites and irons and stony irons may have come from larger objects big enough to form a iron core. But there are those primitive meteorites. We already kind of talked about them a bit when we were talking about rocks. These have never melted. The achondrites would be considered igneous rocks because at one point they melted just enough to separate out the iron. Now, these are chondrites. These have one of the characteristics of them is they have these chondrules, these small spherical grains embedded in them. And one of the really interesting things is that if you'll ignore the elements that are really easy to vaporize, well, volatile elements, chondritic meteorites have compositions that are very similar to the sun. Now, given that two of those easy to vaporize elements are hydrogen and helium, this isn't saying they're mostly hydrogen and helium. This is saying if we look at the heavy elements in a chondrite, special guest appearance from T.A. Percy, but if we look at the elements in a chondritic meteorite, they look similar to what we measure in the sun. Now, there are still classification schemes. Ordinary chondrites, they seem to be the most common meteorite, which mostly just means they're the sort of coming from the sort of asteroids prone to sending rocks into the near Earth area. You also have some enstatite chondrites. You also have enstatite chondrites, which have some really strange chemistry. They are missing oxygen, and their rock chemistry is more on the reducing side than the oxidating side. And carbonaceous chondrites, which are really interesting because they contain a lot of the kind of middling elements, the elements that aren't quite rock, but are not as volatile as like the hydrogen noble gases and stuff. So let's look at a carbonaceous chondrite. This is the elemental abundances of the Allende meteorite. It is the largest carbonaceous chondrite meteorite that we found. So what this does is the bottom scale is abundance in the meteorite, and it's normalized so that silicon is 10 to the 6. So for every 1 million silicon atoms, how many atoms of everything else is there? And that's why silicon's not on this plot. And abundance in the sun, again, for every 1 million silicon atoms in the sun, what are all the other elements? You can see most of them fall on this line. And one of the interesting things is the ones that don't fall on this line are ones we'd expect, ones that we'd expect not to. If you look at the ones that are more abundant in the sun than Allende, got argon, neon, helium, nitrogen, hydrogen, carbon, oxygen. All of those are relatively volatile elements. Those are elements that form chemical compounds or on their own are easy to vaporize. Carbon forms things like methane or carbon dioxide or monoxide. The others are all gases in their normal state, but they also form elements like water or ammonia. So the one that's really obviously more abundant in Allende than the sun is lithium. And lithium is really easy to fuse into something else if you put it somewhere hot, like the sun. So the sun has fused away most of its lithium. that it formed with, but the rest of the solar system still has them. So let's start matching these meteorites to asteroids. So we don't currently have any asteroid samples. We're getting some. The Japanese have a mission called Hayabusa 2 that's going to bring us back some asteroid samples from an asteroid called Ryugu. NASA has OSIRIS-REx, which is going to bring us back something from Bennu. So, but one of the problems is that asteroids don't really have distinguishing spectra. These are spectra of various sorts of asteroids, and we're going to go through them. But I'm showing these just to show a general shape. What you can measure is the albedo, how reflective they are. You can see that plot, what we're graphing against these asteroids. And what's the slope? Are these gray asteroids? Their albedo is the same throughout all wavelengths, or are they red asteroids? Are they getting redder? You know, the albedo is higher in the red or the infrared than the blue. Occasionally you can find absorption bands, like you see Vesta has that dip. Other examples would be Bamberga on this plot, would be Bamberga, Juno, maybe Alpha, maybe Athamantis and Pallas, maybe Ceres. And try to match those up with things. Let's go through some types. So here are some types. Ceres and Bamberga are G-type asteroids. So is 253 Mahilde, which is one of the asteroids we visited with spacecraft. We've also visited Ceres. They tend to be dark asteroids. You notice the scale, their albedo is less than 0.1. There's maybe red. Ceres isn't particularly red. Bamberga is. And these are probably made of materials similar to carbonaceous chondrites, which are also pretty dark. You have S-types, S for stony or silicate, which tend to be brighter, but they also still are pretty red. Again, here are some examples. Juno, Athamantis, and Pallas, we think are S-type asteroids. Eros is an S-type asteroid. It's another one we visited with spacecraft. And we think these are made of silicates. So their analog would be some type of stony meteorite. For at least small asteroids, it's probably going to be chondritic. It's probably going to be a chondrite meteorite. For some of the larger ones like Pallas or Juno, it might be better to use an achondritic meteorite. But they're just, again, they're bright. Their albedos, 0.1 or brighter. They seem to be pretty red. Pallas isn't as red. And occasionally you see kind of absorption bands in them. M-types. Ignore Vesta. Vesta is not an M-type. Psyche is an M-type. So is 21 Lutetia, which is pictured. These are mostly classified as they have moderate albedos and they don't have any really distinguishing features in their spectra. And while some M-types might be the source of iron meteorites, it might be metal, we think Psyche is a metallic asteroid and we're sending a spacecraft to visit it. But asteroids like Lutetia aren't dense enough to be metal. They're just kind of in this category as they look like metal, but they aren't. They're kind of spectrally boring. Yeah, so Lutetia is M-type, but its surface looks like, since we visit with the spacecraft, we can do more detailed work. It looks more like an enstatite chondrite or a carbonaceous chondrite that doesn't have very much H2O in it. Now, Psyche is probably metal, and we're visiting it with a spacecraft. The mission is still called Psyche, and it should arrive middle of next decade. Now, another sort of those enstatite chondrites, the primitive meteorites with really weird chemistry, might be E-type asteroids. We don't have a particularly good picture of one. This is 2867 Steins, which was one of the asteroids flown by a mission to somewhere else. And they look a lot like M-types as well. So kind of the M and the E-types are including both the metallic asteroids and the enstatite chondrites, which are a type of stony meteorite. So they're V-types. V-types are neat because we know where they came from. Not just, stony meteorite, iron meteorite, but which asteroid. V-types are all chunks of Vesta. V for Vesta. They look like stony meteorites, or rather they look like S-type asteroids. but they have a big absorption band. You kind of see it in the picture in the spectra of Vesta at the top. Now, we also have meteorites linked to Vesta. They're called HED achondrites. HED stands for the minerals that make them up with. So there are some pictures of meteorites. We can also see that Vesta has some big craters. That thing at the bottom, that's a crater. You know, it is nearly Vesta-sized. It's also got some smaller ones on top. So that's a pretty good, and we've already talked about in the previous lecture that Vesta has a big asteroid family. It's got a bunch of asteroids that were probably created when something big smacked into Vesta and launched some of the stuff to nearby orbits, and some of the stuff eventually made it all the way to Earth. Now, the other big important type are D and P types. They're dark, they're red, they have no absorption lines. Bamberga is kind of intermediate between a C and a P type, and there's a few other minor types. Again, a lot of the time we're classifying albedo, slope, which is basically is it red or gray, and just spectral lines, because there's really not much we can go on. Now, what our overall goal would be to be able to match asteroids to meteorites. And I've told you a little bit about which ones we think go to which asteroids go to think meteorites. You know, the goal would be to be able to directly connect them, to say, okay, this asteroid is a good model for what we think the Allende meteorite parent body is. But it's hard. I mean, some of it is just that asteroids are out in space and we can't do a lot of the same tests we do with meteorites, short of a complicated, expensive space mission. But the other thing is what's called space weathering. Now, weathering on Earth is the change of things when you leave it out in the environment, in the wind and the water, and you get erosion, you get chemical changes, all that kind of good stuff. Space weathering is when the solar wind, a stream of particle coming from the sun, and cosmic rays, which are higher energy particles that come from the sun and various extra solar system sources. These hit the out parts of rock. There's no atmosphere to shield anything, and they slowly alter the rock. And again, we can see this on, for instance, lunar samples. You can see this is a picture of a soil grain showing that the iron minerals in this rock have changed into metallic iron, which gives it a different look, spectroscopically speaking. Now, for the moon, we can kind of disentangle that because we can see that there's a kind of a crust on the soil grain. Inside is less weathered than outside, so we can make a comparison, but for most asteroids, we're out of luck. And most meteorites have been altered as they came through the atmosphere. For the moon, we don't have to deal with the fact that our samples came through the atmosphere on their own. They were carried by the Apollo astronauts or robotic Russian missions. But we can at least say, even if we can't match them exactly with meteorites, we can still at least use this classification to try to make sense of the asteroid belt. And does seem to be something to this. So for instance, if we look at where we find certain classes of asteroid, this is just as percentage of asteroids. So the main belt, there's a lot more asteroids there, in actual numbers. So the inner belt is mostly S-types, and that might influence why we mostly find stony meteorites. Farther out, the outer belt and other asteroids out there seem to be mostly D and P types. This is kind of before we get to things that are majority icy, but these objects do seem to be quite different from the S-types asteroids that are more like rock, pure rock. Trojan asteroids are in this category. You can kind of see where they are on this plot. And C-types are reasonably common everywhere. They're more common in the mid-belt than anything else by numbers. You can find M-types throughout the asteroid belt. They're not very common. And E-types seem to be in a very particular zone between the main belt and Mars. It might suggest that there was only a few E-type parent bodies or parent objects, or there's something else really peculiar about them. All right, so let's look at TNO spectra, trans-Neptunian objects. Again, we also sort by albedo and redness. This is a pretty easy thing to do. We do it with stars too, but stars are not part of this class, because all you need to do is figure out a way to get the size, which you often can do by making both measurements in visible and infrared. Because for albedo, the visible light will be reflected and the infrared light is re-radiated light that was absorbed. Or if it's big enough, you can get the size from occultations, but there's plenty of ways. So if you get the size, you can measure the albedo, the reflectivity. And you can also get a color by measuring what the albedo is in different filters. So the top is a color plot. We do this with stars sometimes to remove things like interstellar dust, to be able to correct for that. But this is also getting us at the color of objects. You can kind of see the tint to help you guide the eye, that the objects near the origin are pretty gray. They're pretty spectrally neutral. But the objects near the top are red. The ones in yellow are non-trans-Neptunian objects. So we have Phoebe and Triton, which are both moons of planets that probably came from the Kuiper belt or the scattered object population. And you also have like Mars, just as an example of something you can picture that's pretty red. A few things are as red as Mars. Now, what the red is it's not like Mars is red because of iron oxide. The red is thought to be what astronomers call tholins, which are just complicated organic molecules. And we can't break down the exact composition of all of them, but they're, carbon and nitrogen and oxygen and hydrogen in all the complicated shapes that you can do with a big pile of various sorts of ices plus UV radiation. Kind of think of Titan as an example. Now we can also see spectroscopic features. Water ice is very spectrally distinct, so that can tell us something like water ice, or we can identify other sorts of ice. In the bottom plot, we have an example of a lot of large TNOs, large trans-Neptunian objects, and rough estimates of their sizes, colors, and albedos. You can see Sedna is really red on this picture. That Pluto is kind of reddish, but it's a very different color than Charon. Orcus is particularly dark, even though it has a similar orbit to Pluto's, but its moon is pretty light. So here are some examples of trans-Neptunian objects. Now the bottom, the lines are plotted in our spectra in visible and the near infrared. They're staggered so you can see them all on the same plot. They're not, basically each of them had a constant added to it, so they wouldn't all plot on top of one another. The dots are broadband measurements of their reflectivity at a certain band of wavelengths using a filter. So basically those are what you'd get if you took a picture, and the lines are what you get when you take a spectrum. And the top four just have that slope. They're pretty boring. You could see some changes, like the first three look really spectrally similar, but the fourth from the top is much steeper sloped. It would look much redder than the other two. Now the bottom two have bands. They have some of those bumps and wiggles and beyond just a normal slope. Those might mark water ice, and they might mark hydrated rock. So that would be rock that has a lot of water incorporated in the crystal structure. So what we talked about today, we talked about how asteroids, how we classify them, brightness, redness, and presence and absence of spectral features. We don't really have a classification system yet for trans-Neptunian objects. We have some ideas about how to match asteroids to meteorites, but space weathering makes things harder. It would do us good to get some samples back of asteroids that we know which asteroid they are and what they look like spectroscopy. So Hayabusa 2 and OSIRIS-REx will really help with that. TNOs, they don't really have a classification scheme, but we can see spectral lines on some of them, which can tell us things like, is there relatively clean water ice on the surface, or is it just kind of a gray or a red mess of, mostly of those tholins, which are complicated enough they don't have nice clean spectra. So next time we will be moving out of the solar system briefly, because this class is nominally physics of the solar system. I like to throw in some planet stuff because it basically lets us get an alternate view. So we're going to spend a week talking about exoplanets.